vapor cycle systems are loop systems that are used for equipment cooling and air conditioning. These are composed of 4 main equipments: a compressor, a condenser, an expansion valve, and the evaporator. And most of the cooling is coming from the evaporator, where the heat transfer is provided by a phase change of the fluid, which is most of the time a refrigerant. In order to improve the efficiency of such equipment, one of the key issues that remains today is the flow maldistribution that can account for up to 30% of losses. In parallel, in aviation, such systems are still used with Freon, which is a high global warming power fluid. And to fulfill the EU mission of fighting climate change and make aviation more environmental friendly, one of the objectives is to replace this refrigerant by a low global warming power alternative. I'm Delphine Laboureur. I'm an associate professor at the von Karman Institute, and I'm the coordinator of the PANTTHER project, which is an EU project funded by the CleanSky joint undertaking, and it's an acronym for Experimental Multiscale Multiphase Heat Exchanger. The von Karman Institute is in charge of the experimental effort, and Temisth is developing the numerical tools. The project started in September 2020 and is coming soon to an end. Now I will let my colleague Aude to present you the different facilities that we developed.
Hello, I am Aude Lecardonnel, working on the PANTTHER project. I am a PhD student in my 4th and final year. So the first step of the PANTTHER project was to build instrumentation for two-phase flow, such as a capacitance probe to measure the void fraction, but also a venturi flow meter to measure the two-phase flow mass flow rate. This instrumentation was tested on a calibration line that was specifically built for this step. Air and water were used as fluids and were pressurized at 7 bar to ensure similar density ratio as can be found in refrigerant application. So the second step of the PANTTHER project was to test this instrumentation on a simplified evaporator, so basically being a header connected to channels. So the instrumentation was mounted on the channel to be able to measure the two-phase flow mass flow rate inside each channel, and then we were able to assess the two-phase flow distribution inside these channels. Several combinations of parameters were tested, such as we changed the inlet diameter, the inlet position, we put also a splashing grid, an accessory at the inlet to disperse the liquid phase inside the whole header. So we tested several combinations of parameters, and we were able to retrieve their impact on the distribution. The third step of the project was then to build an entire vapor cycle system that you can see behind me. So basically it is a compressor compressing the refrigerant in its vapor phase, then sending it to the condenser that condenses it in its liquid phase, and then sending it to an expansion valve that creates very big pressure drops, and at the outlet of the expansion valve we are able to have a two-phase flow. This two-phase flow is then sent to the evaporator, which is the purpose of the PANTTHER project. So the refrigerant that we used is R1234-E refrigerant, which is a new generation of refrigerant and that has a very low polluting index. So in the first time we tested this refrigerant on a simplified evaporator test section that you can see behind me, which is double heated pipe. So the water is flowing and is outside the refrigerant pipe and is heating up and evaporating the refrigerant inside the pipe. So this is a very simple geometry, but it allowed us to obtain heat transfer coefficient and pressure drop correlation that we compared with the literature, because the thing is that this refrigerant, as it is quite new, is still not fully characterized in the literature. The final step of the project was to test this refrigerant in true and real evaporators that you can see here. So it's an evaporator that is actually used, but that we simply a bit modified. So we increased the inlet pipe diameter to allow for more stratified flow pattern, so to be in the worst condition at the inlet. So we modified it to have more inlet and outlet. The whole section can also be turned to test the change of orientation of inlet and outlet position, and to also check if the conclusions that we had in the previous adiabatic line can be also found for this evaporator. So it is really simply instrumented. At the inlet you can find on both inlet and outlet PT100 that measures the temperature. You can also find absolute pressure sensors. For the air side, the air is coming from the compressed line and then is further sent to an electrical resistance that heats the air up. Then it is further sent to the rectangular section that you can see here. So it is equivalent to, the length is equivalent to around 10 times the diameter to ensure a stabilized flow at the inlet. We also put some honeycomb at the inlet of the test, the rectangular section, to be sure that we have a stabilized flow. Then the pressure drops on the refrigerant side and on the air side is both measured through validin differential pressure sensors that you can see here. At the outlet of the test section, we also have on the air side 4 racks of thermocouples to be able to have information about the distribution of the temperature of the air at the outlet. So the objective now of the test campaign is, as I said, to be able to test several header and several header orientation and inlet outlet position, and also to place at the inlet on the refrigerant side the same splashing grids that we tested on the adiabatic line.
As the only woman full-time professor in the von Karman faculty, I was really honored to have been awarded this grant agreement from the EU to develop further our competence in two-phase flow heat exchanger, but also to help other young women researchers to develop their competence. In the PANTTHER consortium were 3 women, 4 men, coming from 3 different nationalities, and this very diverse team help us to work efficiently and bring more innovative ideas.